Okay, so we're going to start the review for Chapter 12. A researcher wants to know if there's a clear leader among the 5 most popular manufacturers of laptop computers, or whether they are all approximately equally popular. She asked a random sample of 250 people which brand of computer they trust most. These are the results. Which of the following is appropriate null hypothesis? So null is there's nothing unusual going on. No computer's, better than another computer. They're all about the same. So null would be, you want to say this in words, so I'm leaning probably not towards A there. The people in the population are equally likely to identify each of the 5 brands as most trustworthy. So most popular, not whether they are approximately equally popular. So I'm leaning towards C. Let's just look at the rest. B is definitely gone. For at least one of the brands, the proportion of people in the population trust this brand is different. No, that's not the null. The observed counts are equal to the expected counts. That's definitely not the null. So A is tempting, but it's got to be C here. And we really prefer to say it in words. Random samples of male and female high school students were asked to identify their favorite food group. Here are the results. Expected counts for each cell are given in the following table. Okay, so these are all the expected counts. So these are the expected here, I guess. Which of the following represents the individual component of the chi-squared contribution by the cell? So it's basically, do you know the formula chi-squared equals, observed minus expected squared over expected. Of course, this is on your formula sheet, right? So it would be observed minus expected. And you see the numerator is squared. So the denominator is not squared, the denominator is not squared, the denominator is not squared. It can't be one of those. The observed is 20. So that goes here. And the expected is 21.2. So that goes in both of those spots. So it's got to be D. So just knowing your formulas, that is on your formula sheet, though. You can just follow your formula sheet. So this information goes with both questions 3 and 4 here. So do male and female children respond differently to colors? The study of color association in children asked separate random samples of male and female 4th graders what emotion they associated with the color red. Here are the results for the group. So some people, thought love. Some people thought pain and anger. I guess that makes sense. It could do different things depending on what you're thinking about. Which of the following would be an appropriate null hypothesis? Okay, so let's just kind of look at them, start eliminating. The distribution of emotional associations with the color red is the same for male and female 4th graders. Okay, so that looks tempting. B is definitely wrong. It's not dependent. It's null is nothing's going on. There's no difference. Emotional association with the color are independent of gender. Ooh, interesting one. So A and C are both interesting. The number of observations in each cell is the same for each emotional. No, I don't think that makes sense. 25%. No, I don't think we're comparing. We're not saying they're all equally likely. I think we're comparing genders here, right? So since we are comparing genders here, it's either going to be A or C. So it does seem like the distributions are going to be the same for male. There's nothing unusual going on, so I think A is the better answer here. Chi-squared test statistic for this data is chi-squared is 4.629. Which of the following contains the p-value for this test? The chi-squared, if you remember, chi-squared is always skewed to the right. You got some value there, 4.629. You're shading to the right always with chi-squared. And so to find the p-value, for this one, you're going to use your calculator menu, statistics, distributions, and we're going to go to chi-squared CDF. And so the lower bound is 4.629, upper bound is infinity, and degrees of freedom. See the info above. So there are 4 categories. So categories -1 times rows -1. So 4 minus 1 is 3. 2 minus 1 is 1. So 3 times 1 is 3. So I think it would be 3 there. and we get 0.201, so 20 point, so greater than 0.1, so we think it's going to be E. Using a computer, I randomly select 1,000 numbers from a standard normal distribution. I classify these numbers according to whether the values are at most -2, between -2 and 0, between 0 and 2, and at least 2. The results are given in the table below. So I've classified them. The expected counts based on empirical rule are given as well. So they did the expected counts for us. It's pretty nice. These look like expected count formulas almost, like just looking at it. Remember, row total times column total divided by the grand total. But that's not what we're finding here, I don't think. So I don't think those are going to be the answers. To test to see if this distribution of observed counts differs significantly from the distribution of expected counts, we use the chi-squared. So what is the following component of that? So again, it's observed minus expected over expected. So this one doesn't match there, so that can't be it. So it's got to be this one. It's the only one that's really the right form there. Fitness can be measured by rate of oxygen consumption during exercise, with more fit people having higher rates. Unfortunately, the measurement is quite costly to obtain, so a study done to see if this measurement could be predicted from time it takes in minutes to run 1,500 meters. Oxygen consumption was measured on a random sample of 30 students. Their finish time on a 1,500 meters was recorded. Some of the results of a computer regression are given below. So they did a regression for this one. You've seen this. Which is the appropriate interpretation of this number? So remember, this one is the y-intercept. This one is the slope. So slope is rise over run. May not be obvious in this one what stuff is. So the variable, the run time, that's always the x variable right there. So I know run time is the x variable. It just helps to know this when you're about to do this problem. And then the y would be the time I think it takes. So, okay, so the slope of -3.2088 divided by 1. So every time the run time, maybe, let's see, what are we measuring here? Is it time? It's oxygen consumption, right? So this is oxygen consumption right there. Sorry about that. Time is the x-axis. I just messed that up. Okay, so every time the run time, that's the denominator, is x, increases by 1, the oxygen decreases by 3.2. Okay, so an increase of runtime of 1 minute decreases predicted. So that might be it. I'm not sure about the units. I haven't looked at it. Increase in oxygen of 1 minute decreases production by 3.22 on average. Predicted. So because this is oxygen measurement, I don't think this one works. An increase in runtime by 1 minute. Increases, no, it doesn't increase, it decreases, it's negative slope. One associated with a decrease in predicted oxygen by 3.2%. I don't think that's a percentage there, no. Runtime of 10 minutes corresponds to predicted oxygen consumption of 32.088. I don't think that makes sense, it's got to be A. That was the one I was leaning towards to start with there. Are high school students who like English class more likely to enjoy their history class as well? Here's a regression analysis for 30 randomly selected students who are asked to rate how much they like both English and history on a scale of 0 to 5. So I don't know if it'll make a difference here, but the English is the X because it's listed here. That's always our X right there. English is here. I guess the history would be the Y-axis that we're measuring from 0 to 5. Estimate of the standard error of the slope. Remember, the slope is going to be the 0.5 there. So standard error is going to be this guy, the one right next to the slope. Just like T for the slope is going to be that one, p-value is going to be that one, depending on whether if it's one-sided, you divide by 2. If it's two-sided, that's it. So the standard error is 0.1, that one right there. A stat-minded English teacher wonders if she can predict the lengths of essays that her students submit on the basis of how large the computer files for the essays are. She selects a random sample of 13 student papers, all produced by the same word processing software. and compiles and compares file size to the word count for each. The computer regression analysis of our data is given below. My guess is this is pretty close. I don't know. I'm just guessing. So file size is your X here, file size. And I guess this is like word count here. I just like to think about that. So X is always that guy. Okay, what's the estimate for the standard deviation? So standard deviation is this guy, right? So 145, so not standard error, 145, so it's one of those guys, right? The average distance between the file sizes and the mean is about 146 kilobytes. Average distance. The average distance between the word counts of each of the essays and the mean word count is about 146. Predictions of word counts for files in this regression model will be off by an average of 146 words. So this is an interesting one. Remember, if we were to write the equation, it would be y hat equals a plus bx. We're predicting the y value. The fact that this one says predictions, because we're talking about the regression line, you got to go with that one. They were very similar in a lot of ways, but the one that says predictions, that's the one, because we're predicting the y value here. We're predicting the word count, the y value. Which of the following conditions must be satisfied in order to perform inference for regression of y on x? For each of the explanatory variable y, the x values vary accordingly to a normal distribution. The standard deviation of the population of y values for a given value of x is the same for every x value. Individual observations are independent of each other. Okay, so independence, this one is maybe the most obvious that's got to be it. So if I see 3 as part of it, I'm leaning towards, these two are out because it's got to be 3. 2 looks pretty good. The standard deviation of the population of y values. So isn't this kind of like equal standard deviation, right? Where the above the regression line, below has to be about equal. So 2 looks good. So now I'm eliminating that one. For each value of the explanatory variable y, the x values vary according to a normal distribution. I don't think that would be true. Lots of times we even just say like, has to be no major skew, no obvious outliers. So I don't think it's going to be that one. I think it's got to be D. That was a tough one, though. It's at least tempting to put that. That's what they're trying to do, make it tempting. A high school guidance counselor wonders if it's possible to predict a student's GPA in their senior year from the GPA in the marking period of their first freshman year marking period. She selects a random sample of 15 seniors, records their full GPA in the senior year, and their first marking period GPA of their freshman year. It did a regression. Okay, so the guidance counselor wants to test the hypothesis that the null is there's no association here, like between the two, the slope is 0. And the alternate is there is an association here, right? There's something's going on here. It's either positive or negative, they're basically saying, at the 1% level. Which of the following is the appropriate conclusion? So the p-value would be this, right? And we don't have to divide by 2 because it's not a one-sided test. So that is the p-value. That is the p-value. So 1.1 is above the 1% level. So because the p-value is greater than the alpha level, I fail to reject, right? There is not convincing evidence. So there is convincing evidence is wrong. Is greater. This looks tempting. Let's just look at the rest of them. We accept that we never accept the null. That doesn't look right. Because p-value, no, those aren't the wrong p-values, so it's got to be B. Okay, do you straighten up your hotel room before checking out? This question was asked of a random sample of 232 men, 284 women who travel frequently in business. Depends what you mean by straighten up, but a little bit. Do these data provide evidence that there's a difference in the response between men and women? Is there a difference in the response? So is there a difference? So this is a test of sameness or homogeneity. So this is that kind of chi-squared test. You can see the two-way table is another giveaway that it might be that. So let's just start. So the null would be that there is no difference between men and women. I'll just say this in words. And whether or not they clean their hotel room. The alternate is there is a difference between men and women and whether or not they clean their room. So then let's just start with the conditions here. So call the name of the test. This is a chi-squared test for homogeneity. Okay, and then you're going to go to the conditions liner, sorry. The first one is linear though. So linear, is this linear data? So we just did that section, and this is when you have computer output and it's all about the linear regression. This is not that test, so that is not the conditions there. The first condition is random sample, unless it's an experiment, and it was a random sample, so you draw a line there. Random sample. The independence condition is less than 10%, so 232 is greater than 10%, or less than 10% of all men, and 284 is less than 10% of all women. Sorry, this is so sloppy, you get the idea though. And then expected counts. So to do this one, you really probably want to go to your calculator and let's just get the expected counts. We could do the expected counts by hand. Let's see what the first one would be. So if we did it by hand, it would be 232 times 257 divided by 516. And that should give us the first expected count. Let's do it in the calculator. So if we go to, whoops. So if you hit the template key next to number 9, you can choose a 2x2 template right there for matrix. We're going to do 130, 127, 102, 157. We're going to store that control variable as travel. Okay, so now let's do the chi-squared test here. So menu 6.7, chi-squared two-way test is a two-way table here. And we're going to choose the travel matrix. Okay, and to see the expected matrix, you hit the variable key and go to expect matrix. And those are the values. Remember, we did that a minute ago, and I think that was the same expected value we got. So I would write those in here. So just write, 115.55, 141.45. Sorry, so sloppy. 116.45, and then 142.55. So you kind of write those in there so you have them. And now when you say all expected counts are greater than or equal to 5, you have them shown somewhere on the paper, so that counts. So those are your 3 conditions that you've got there. So degrees of freedom would be rows minus 1, categories, so it's categories minus rows minus 1 times columns minus 1, which would be degrees of freedom is 1. That's kind of weird. So we could do the chi-squared value here. We could start showing our test statistic here. So chi-squared equals, and we would just start it, the observed 130 minus expected of 115.55 over the expected plus, and then we do the next one, 127 minus 141.45 over 141.45 plus ... and maybe do the last one as well. But the chi-squared statistic is, we got it from our calculator, is really 6.54. The Degrees of freedom is 1. We got that from we also could get it from our calculator. It's there. And the p-value we need to put on there is equal to 0.01. Okay. And this, again, somewhere on this, say what it is. It's a chi-square test for homogeneity. And so because our p-value is, let's see, I'm guessing 5% here. So less than 10% of 1% is less than 5%. We do reject the null. We do believe there is a difference. We do have evidence to say there's a difference in the responses between men and women regarding cleaning up your room when you're traveling. If you want to see the answers as chosen by them, this is the answers for that one. So let's see if we missed anything. Looks pretty good. So you can just say that distribution of response is not the same for both genders. There is a difference. Looks about right. Okay, 12. A game of chance involves rolling 2 dice. A player plays $5 to roll 2 dice. If 1 6 is rolled, the player wins $10. If 2 6s are rolled, the player wins $40. Savvy observer believes the die is biased against landing on a 6 and keeps track of the outcomes on a random sample of 216 plays of the game. Just stood there and just watched. If the game is fair, then each toss should result in 0, 1, or 2 6s with probability of 25 out of 36, 10 out of 36, or 1 out of 36. The actual counts for each of these 3 outcomes is shown in the table below. Carry out a test to determine if the game is not fair. So first of all, so I guess these are the expected counts. If the game is fair, we would expect these counts, right? Those are the expected counts. So we kind of had the observed counts. We have the ratios. Those are not actually the expected counts. Okay, so we have to figure out the expected counts when we do this. Okay, I don't know if you've identified the test yet, but because of the variables here, you really just have it's just a goodness of fit, right? You've got the distributions will be what we expect them to be here. We hope this is a fair game. So I think the null is this is a fair game. That we expect nothing unusual. This is fair. The alternate would be it is not a fair game. So this is a chi-squared goodness of fit test. To figure out the expected values, we really need to do that. Let's add up the numbers. I don't know if they told us. Oh, 216 plays. So if the first one is 25 out of 36, so 25 divided by 36 times 216. So we would have expected 150 here. And then for the second play, it was 10 out of 36 times 216. We would have expected 60, but we got 50. And the last one was 1 out of 36 times 216. We expected 6, but we only got 3. Okay, so I think they're a little bit different. Let's see what happens. So let's check the conditions. So this is hopefully either a random sample or random assignment. Let's see. Random sample. So random sample. The independent condition is less than 10%. So, I mean, I don't know if you have the less than 10% actually here. I think each roll is independent. Each roll is not affected by the previous roll. Rolls of the dice are independent, so I think you could just say something like that. Each roll is independent. And then expected counts. Expected counts are all greater than or equal to 5. We already listed them, so they're all barely greater than or equal to 5. One of them 6. So those are your conditions. The chi-squared test statistic. is going to be the observed 163 minus 150 squared over 150 plus the next one would be 50 minus 60 squared over 60 plus 3 minus 6 squared over 6. And let's do this one on our calculator. So let's see how to do this. So if I don't really remember, let's see, 6, 7, chi-squared gives us a fit. What do we need to have here? Observed list and expected list. So we need to have those two lists. So go to your, it's been a while since we've done that, right? So you can go there and kind of look at it. So I just usually call observed. If it pops up, I might go to a new problem, doc, insert problem. So I don't have any left over from previous variables. And so I just always call them OBS and expect. There are 3 observed, 163, 50, and 3. And the expected was 150, 60, and 6. So now let's go back to that calculator page. Go menu, 6, 7, goodness of fit. Choose the observed, choose the expected, and degrees of freedom would be categories minus 1, which is 2. There you go. If you want the comp list to see which one was the biggest contributor, if they asked about that, you would go variable and do that. You can see that the middle one was the biggest contributor there, rolling the number of 6s as a 1. Okay, so we get chi-squared equals 4.29. Degrees of freedom equals 2. The p-value equals 0.116 or 117. So because our p-value is greater of 11% or almost 12% is greater than our alpha level of 5%, we fail to reject the null. We don't have enough evidence to say that this game is unfair. Let's see what they said for number 12 for their answers. Game's not fair. They list out 2 possible null and alternates. We used words, which was fine. This one, did we miss anything? We fail to reject. There's not convincing evidence that the game is not fair. Perfect. Okay. And finally, the last question. So they've got a whole bunch of data here for us. Professor Breedy asked a random sample of 10 of the 250. So I'm just going to underline that because I'll need that in a minute. 10 of the 250 students in her introductory class to record the total amount of time and hours they spent studying for a particular test, and also record a student's score on the test. She then performed a regression analysis of the data. Below is numerical and graphical output. Great. Using computer software, discuss whether the conditions for inference have been met. So you don't have to describe what further information will be required. Oh, interesting. Okay. So liner is the thing. So linear. So this looks linear, and the residual plot right here is scattered, which also shows linear. So linear, check. You would say that maybe in words, what I just said. Independent, so less than 10% condition. So it looks like we 10 of the 250 students. So 10 is less than 10% of the 250 students. So less than 10% or independence condition met, independent. Okay, N stands for normal or approximately normal. So, we don't have, this is the residuals. Okay, so I was really expecting them to give us the data. So what we're missing here is a plot, histogram of the data. So we need a histogram or some type of representation of the data to see if it's approximately normal or at least not majorly skewed and no outliers. So that's what we need. E is equal distribution. That looks about right. Above and below looks somewhat equally distributed. And R, random sample, we kept that. Let's see what they said for 13 for part A, for how they said it here for that one. So A normal probability plot of the residuals showed no strong skewness or outline. Okay, so that's what that is. So that's a normal probability plot. We haven't talked about that a lot this year. It's actually not part of AP Stats, like you don't have to know how to use it, if that makes sense. But this guy right over here is called a normal probability plot. And so if that's pretty straightish, which it is, that means the data is linear. Again, that's not part of AP Stats, so I don't expect you. I think you would have gotten credit for what we said here. You need a histogram or something because it's not part officially of the AP curriculum, although we sometimes learn it. You can use it, but you don't have to know how to do it. For the remaining questions using the data, assume the conditions for inference have been satisfied. Do these data provide convincing evidence that there is a linear relationship between study time and test score? Okay, so we're going to do a test here, right? So we've got that taken care of. So let's look at the data here. So we know that the t is equal to 4.25. It's from this, because this is the slope. So that's the t value of the slope. The p value of the slope is that if it's, let's see, what's the null and alternate in this one? So they spent time studying particular test scores, student scores, the numeric and graphical output of your student software. So the null is, beta equals 0. So in other words, like there's no real relationship between these two. Do these data provide evidence there's a linear relationship? So they didn't ask for a direction here, just is there a linear relationship? So I think that's not equal to, right? So beta is not equal to 0, but it's linear, right? So because it's not equal to, we can actually take this value right here, our p-value, and just use it. Like we don't have to adjust it at all. So our p-value equals 0.003. We don't have to divide by 2 because it's not equal to. And then I always like to put degrees of freedom here in our do section. Degrees of freedom is I don't think we need to put degrees of freedom. We do need to probably define the variables. So B or beta is the true slope of the population regression line. X is the study time and Y is the grade. So those are just defining the variables. Just don't forget to do that. Okay, so what's our conclusion going to be here? So we're going to say because the p-value of 0.003 is less than the alpha level of 0.05, we reject the null. We do have evidence to say that there is a linear relationship between study time and grades. And it actually seems to be positive, but that's not what they asked. Construct and interpret a 95% confidence interval for the slope of the population regression line for predicting test scores from study time. Just get a totally different frame of mind for a second to do interval for the same type of data there. Okay, so here's our formula. So we're going to go with, let's get our slope here so slope is 12. So 12 plus or minus. So 95%. So if you do that t critical value, this is 95. So there's 2.5 over here, 2.5 to the left. So to find that, we use the inverse t command. So menu 65 inverse t, and you're going to put an area of 0.975 and degrees of freedom. Let's see, seems like we had 10, so 10 degrees of freedom is 10 minus, it's been a long time for this one, you have to get this straight. Degrees of freedom is n minus 2, so 10 minus 2 is 8. So you're going to put in the 8 here. And you get 2.306 times standard error of the slope we're going to get from the data here. So standard error of the slope was this guy right here, 2.825. 2.825. So you're going to type that into your calculator at this point. So 12 plus 2.3 times 2.825. Change that to a minus. So we have an interval from 5.5 to 18.497. Okay, so we have an interval. So we are 95% confident that interval from 5.5 to 18.49 contains the true slope of the population regression line for this data in context. Let's see what they said. We are 95% confident the interval for all students in the introductory stats class. Okay, and I think they showed pretty similar stuff. They did define the variables again. We've done that already up there, but always a good idea to define those. And t interval for the slope. Morning.